Welcome to part 2 of aromaticity. Here we have examples of heterocyclic aromatic compounds. Why are all these aromatic? Because each one has an odd number of pi electron pairs in its cyclic cloud of pi electrons. All 5 of these, as you can see. You will see that purine and pyrimidine in your study of biochemistry. You can see here quinoline has 5 pi electrons. 1, 2, 3, 4, 5. Indole has 5. Imidazole has 3. Purine has 5. 1, 2, 3, 4, 5. The electron pairs outside the ring, as you can see here in purine, are not pi electrons. Pyrimidine has 3 pi electron pairs, 1, 2, and 3. Of note, purines and pyrimidine substituted compounds are found in DNA and RNA. The purine and pyrimidine substituted compounds make up the structure of DNA and RNA, the partial structure of those very large molecules. But adenine and guanine are purines, and cytosine, uracil, and thymine are pyrimidines. And adenine, thymine, guanine, and cytosine are found in DNA, and the same 4, except in the place of thymine, uracil is in RNA. But all of these are aromatic compounds, as you can see. So let's go to the next slide. You can see here the effect of aromaticity on the pKa values of some compounds. And noticing here, why is the pKa of cyclopentadiene so much lower than that of the pKa for ethane, 15 versus 50? A pKa of 15 is very low for a hydrogen that is bonded to an sp3 hybridized carbon. There's the sp3. Now, to answer this question, we must look at the stabilities of the anions formed when the compounds lose a proton. Now remember, the strength of an acid is determined by the stability of its conjugate base. The more stable its conjugate base, the stronger it is as an acid. Notice that all the electrons in the ethyl anion are localized, as you can see here. However, in the anion formed when cyclopentadiene loses a proton, it fulfills all the requirements for aromaticity. It is cyclic, planar. Each atom in the ring has a p orbital, and the p cloud, or the pi cloud, has 3 pairs of delocalized pi electrons, 1, 2, 3. The negatively charged carbon in the anion is sp2 hybridized. In the following slide, the resonance hybrid shows that all the carbons in the anion are equivalent. So here, this is the acid on the left. The conjugate base are shown on the right, and we have an sp3 carbon here, and we have an aromatic cyclic planar structure in the cyclopentadienyl anion, whereas up here the ethyl anion has all localized electrons, and obviously this one here is, because of its aromaticity, is more stable. Let's go to the next slide. Here you can see the resonance hybrids. The resonant hybrid is shown, and all the resonance contributors. Each carbon has exactly 1/5 of the negative charge associated with the anion. So because of the aromaticity, the cyclopentadienyl anion is a very stable carboanion. This is why cyclopentadiene has a very low pKa. That's the reason. It is the stability given by aromaticity of the cyclopentadienyl anion that makes the hydrogen much more acidic than hydrogens bonded to other sp3 carbons. Let's look at the molecular orbital description of aromaticity and anti-aromaticity. As you see on this slide, this diagram, there are 4 panels, A, B, C, and D. Let's look at each of these a little closer. The molecular orbital theory helps us explain why a planar molecule with an uninterrupted cyclic pi electron cloud is highly stable if it has an odd number of pairs of pi electrons, but highly unstable if it has an even number of pairs of electrons. Now let's look at these panels closer, A, B, and C, and D. A is showing the pi molecular orbitals of benzene, which is aromatic. B is the cyclopentadienyl anion, and it's aromatic also. C is cyclopentadienyl cation, which is non-aromatic, and D is cyclobutadiene, which is non-aromatic. The 6 pi electrons of benzene, displayed here, they occupy 3 bonding pi molecular orbitals. The same thing occurs in cyclopentadienyl anion. Notice that aromatic compounds with an odd number of pairs of pi electrons have completely filled bonding orbitals, and no electrons are in the non-bonding or anti-bonding orbitals. Note, this is what gives aromatic molecules their stability, and this is a key point. Notice that these 3 pairs of pi electrons are in bonding orbitals, not antibonding. Also in the case of the compound shown here, cyclopentadienyl anion. Anti-aromatic compounds have an even number of pairs of pi electrons. Either they are unable to fill their bonding orbitals, or they have a pair of pi electrons left over after the bonding orbitals are filled, as in cyclobutadiene. The unpaired electrons are responsible for the instability of anti-aromatic molecules. Now let's look at a little nomenclature on the next slide. As you can see here, the structures of the following mono-substituted benzenes have to be memorized. Here are the structures of those 4 earlier structures we were looking at, comparing benzene and cyclopentadienyl anion, cyclobutadiene, and so forth. But here are the structures that you need to memorize. Toluene, phenol, aniline, benzene sulfonic acid, anisole, styrene, benzylaldehyde, benzoic acid, benzyl nitrile, and there are others that are listed right down here as well, which include the isopropyl benzene and sec-butylbenzene and 2-phenylbenzene. So those are names that you will need to commit to memory. Aromaticity influences chemical reactivity, as you can see in the slide. This is another example of the influence of aromaticity. In general terms, alkyl halides tend to be nonpolar covalent compounds, so they are soluble in nonpolar solvents and insoluble in water. However, cycloheptatrienol bromide is an alkyl halide that behaves like an ionic compound. It's insoluble in nonpolar solvents but soluble in water. Here it is displayed on the left. Notice that is an sp3 carbon right there. It is ionic because its cation is aromatic. The alkyl halide is not aromatic in the covalent form because it has an sp3 hybridized carbon. In the ionic form, over here on the right, the cycloheptatrienol cation, or tropium cation, is aromatic because it is a planar cyclic ion. All the ring atoms are sp2 hybridized, and it has 3 pairs of delocalized pi electrons. Being more stable, the alkyl halide will exist in the ionic form. The resonance contributors, shown here, and resonance hybrid show stability in the ionic form. And with this many resonance contributors, certainly makes the ionic form more stable. It's soluble in polar solvents such as water. This is aromatic. This is non-aromatic on the left. Okay, let's go to another slide here. So, let's look at anti-aromaticity, the definition specifically. Stated here, a compound is anti-aromatic if it is a planar cyclic compound with an uninterrupted ring of pi cloud, but it contains an even number of pairs of pi electrons instead of an odd number. So, very significant. It can meet all the requirements of aromaticity, but if it has an even number, it is very strongly anti-aromatic. Keep in mind that aromaticity is characterized by stability, whereas anti-aromaticity is characterized by instability. An anti-aromatic compound is a planar, cyclic compound with an uninterrupted ring of p orbital bearing atoms, and the pi cloud must contain an even number of pairs of pi electrons. Huckel would say it must contain 4n pi electrons, an even number of pairs of pi electrons. Cyclobutadiene that we saw earlier is a planar cyclic molecule with 2 pairs of pi electrons. It is anti-aromatic and highly unstable. And thinking of its structure, 4-carbon cyclic compound with 2 double bonds. It's very unstable because of the small number of carbons making a cyclic structure and the even number of pairs of pi electrons. Okay, let's stop here for part 2.